Okay, so welcome to class. We are here in week 2. Thank you guys for showing up. So we've got Brittany, Logan, Matt, and Morgan. That should be good. We get 4 people. Hopefully you guys are all ready to be engaged today. So you can type in the chat box if you'd like, or you have your lovely microphones. So feel free to unmute yourself to chat at any point in time. That'd be great. I think I've got this figured out where I can, and you guys can all see the PowerPoint. So this should work a little bit better than last week. I played with it. So hopefully it works. This week we're doing 3 sections, 3, 4, and 5. Web Work 2 is due tonight at this point, but we are still having some slowness with web work. So I've been monitoring my emails. I've been telling my face-to-face students to email me if they're having issues with web work, and it's getting slower as the day goes on, but it's still working. So as long as it's still working, we're going to go ahead and keep that due date. I hesitate continuing to move back the due date for these because they're going to start piling up, and that just is no good for anybody. So if we need to move web work 2, I will send out another mass email. So just be checking your email periodically. If you're working on it later and web work isn't loading, shoot me an email because that's the only way I'm going to know if things are working or not. So just keep me in the loop. Most people are doing that pretty well right now anyway, so that's good. But 3, 4, and 5, you got those web works due next week. Quiz 2 is due next week, and the discussion board, which again, you can do the discussion board after we finish this live session today. So not too bad once you get going. Yeah. Any questions before we get started on anything from last week or anything that you might have started for this week, or just anything in general? Okay, the one thing that I do want to, before we kind of get going in the PowerPoint, one issue that people are having when you go into the course, right, there's only one way to access web work right now, and that is through the web work button here on the left side of the screen. If you use any, there are other links, but none of them are live because we threw in this new button. So you have to use this web work button on this side. This is what takes you to the correct link in web work, and it opens in a new tab. Have to use that button, and it works best in Chrome. So if you're using an iPad or a MacBook, download the Chrome browser. Safari is horrible. It just doesn't work at all. So make sure that your Chrome is the best, and we can kind of go from there. So, okay, back to the PowerPoint. All right, so let's go ahead and move on. Section 3, as usual, interrupt me if you have questions, typing or chatting, either one is great. But we're going to start in Section 3 with scientific notation. So what can anybody tell me about scientific notation? Just anything at all. When I say that, what comes to your mind? Or does anything come to your mind when we're talking about scientific notation? Powers of 10, good. That is definitely a good thought, because that has a lot to do with it. Anything else? Any other thoughts? No? Okay, that's fine. That's a good way to get it started. So basically, in general, scientific notation is a way to write really big numbers or really small numbers. It's more concrete. It makes life a little bit easier. And we have fantastic calculators that can do a lot of math for us. But if you change numbers to scientific notation, we can play with smaller numbers, which is always easier. You're less likely to make a mistake if you're dealing with smaller numbers. So when we're talking about scientific notation, right, the basis of scientific notation is that we're going to have a number multiplied by a power of 10, as Logan mentioned. Now, with this, the number at the front, right, this number must be between 1 and 10. So you might hear somebody say, you've got to have a non-zero number in front of the decimal, right? Because a lot of times, right, you might have like something like 4.3. So you only want one number in front of the decimal point, and you want it to be not 0. So anything 1 through 9. Okay, so that's just an example. This exponent can be positive or negative. When it's a positive exponent, that's when we have a big number And when I say big, big means the number is bigger than 10. So anything larger than 10 is considered a big number for scientific notation. And if you have a negative exponent, that means we have a small number, and small number means less than 1. So you kind of think of it as 1 and 10. Between 1 and 10 are your beginning number, and so those are your parameters. Anything less than 1 is small. Anything bigger than 10 is big, and that's what we are going to play with here in section 3. All right, let's go ahead and play. So, okay, so we're going to go both ways. We're going to go 320,000 to scientific notation, then we're going to go from scientific notation to standard form. So standard form is the way most normal people talk, right? Scientific notation, we usually don't speak in those ways. So when we're looking at this first one, 320,000, changing that to scientific notation, our goal is, recall, to have a number that is something between 1 and 10. So let's start with this first question. Right now, my number, as you see it, 320,000, where is the decimal point in that number? 320,000. 3.2. Thanks, Matt. So we're going to, we want the decimal to be between the 3 and the 2, right? This is where we want it to be. And the decimal point, if you don't see it, it starts at the end. So when you're thinking about changing this to scientific notation, we want our first number to be 3.2. All right, we're going to take that times 10. Now thinking through, 320,000 is definitely bigger than 10, and therefore it is a positive exponent. And then you have to count. So I always tell people, if you can count, you can do scientific notation. You always start with, where's the decimal start? Where do you want it to be? So I count 1, 2, 3, 4, 5. Moved it 5 places, so my exponent is 5. And now I have an answer in scientific notation. Okay, similar to that, if we're going to go to standard form, what does this exponent of 4 tell me to do? Think about getting out of scientific notation and going to standard form. Yep. Hey, good. Got a bunch of people on that one. Yeah, so move the decimal 4 places, true, and then Brittany threw in, we're moving it to the right, which is very, very important. Positive exponent means our number's getting bigger. If you move your decimal to the right, that's what's going to make my number bigger. Now, I'm going to redo this here. If I have 1.75 and I'm moving it to the right 4 places, I have what I call humps. What goes in these empty humps? Zeros, exactly. So in standard form, this is 17,500. And for the record, WebWork does not like commas. So if you were writing this in WebWork, you would just type 17,500 without the comma. All right. Pretty straightforward there. All right, I want you guys to try 2 of these just to make sure we're all on the same page. Oops, wrong button. Okay, go ahead and try that one. Ooh. Try those 2. First one is just a little bit different, going to make you think a little bit. All right, and I never know how much time to give because I don't know how to tell if people are done. So we're going to just go ahead and start chatting. There's a couple ways to do this first problem. All right, which Brittany is on the right track, but slightly off. When you see million, and this actually is, if you struggle with million, billion, trillion, how many zeros does that mean? That's the very first video of section 3. I would recommend you watching that. And it talks through kind of the numbers and how they work. But Brittany is absolutely right that million means 6. So if I have 43.4 million, that's the same as 43.4 times 10 to the 6th. Unfortunately, that is not scientific notation. So if you think about this, 43 is bigger than 10. Bigger than 10 is positive. Positive goes up. And when I teach this in class, right, I like raise the roof, right? So bigger than 10 is positive, positive goes up. So if I move my decimal one place, because I need that to be between 1 and 10, because it's positive and goes up, that means my exponent's going to go up. And it's going to go up as many places as I move my decimal. So since I only move my decimal one place to get 4.34, my exponent only goes up one place and becomes 10 to the 7th. And I think that's the easiest way to kind of do that problem. So see if that makes sense. And if we need to do another one, we totally can. We got time. We got time. Okay, but does that make sense? Everybody understand where that came from? How we went from red to blue? Okay. Thank you for the feedback. I appreciate it. Okay, and then the last one here, convert 3.58 times 10 to the 3rd to standard form. We're going to move it 3 places to the right because it's positive. So 1, 2, 3. I only have one hump, so I end up with 3,580. Right? Questions about scientific notation? Okay. And as I'm sitting here, I'm realizing that I need to add a slide because you're going to get to homework and we're going to have an issue. So what we're going to do is we're going to do a problem. We're going to do a multiplication problem. So we're going to take 3.1 times 10 to the 3rd. And then we're going to multiply that by, I don't know, 6.32 times 10 to the 4th. Okay, so we're going to do this problem. This works, the process that we're dealing with now works the same with multiplication and division. Exponential rules are slightly different, but I trust that you'll be okay. So the first things first is we're going to multiply, right? Multiplication is commutative, meaning because we are multiplying all these numbers together, it doesn't matter what order we multiply them in. So I'm going to take 3.1 and I'm going to multiply by 6.32. So 3.1 times 6.32 gives me what? Anybody multiplying? If I multiply those two numbers, thank you. We got 19.592. That's good multiplication. Then, right, times 10. Exponential rules. If I multiply with the same base meaning 10, right? What do I do with the exponents? Multiply same base. I do what to the exponents? You add them, exactly. So I take 3 plus 4 and I get an answer of 7. Okay. First issue with this problem is that our answer is not in scientific notation. So just what we got done doing, right? 19 is bigger than 10. Bigger than 10 is positive. Positive goes up. So if I move my decimal one place, I move my exponent up 1, and I get 1.9592 times 10 to the 8th. All right, now this is good math, and we just did great math, and then you type this into WebWork, and it says you're wrong. Okay, and this is what I want to make sure we talk about. There are videos in WebWork to go through it, but we're here, we might as well talk about it. WebWork in this section, when you multiply and divide scientific notation, it uses something called significant figures. And if you look back at my red numbers in our original problem, 3 and 1, this number has 2 significant figures. This one, 632, has 3 significant figures. If they're the same, that's easy. That's how many you want. Ours are not the same. 2 and 3 are different. We always take the least number. So I want my final answer to have 2 significant figures. So when I look down at my answer, I start on the left, 1, 2. That means I look one place past, I'm going to round. And since I'm looking at the 5, 5 rounds up. So 1.9 is going to become 2.0 times 10 to the 8th. And that is the answer that WebWork wants because it's using significant figures. Okay. If you're looking at this right now going, I don't have any idea what she just did, right? It's about rounding, but the significant figures tell you how many places you want. Every one of those problems in WebWork, I'm pretty sure, has a video where it talks you through significant figures and how to use it. You know, the videos are like 1.5 minutes or 2 minutes long. So if you get stuck on the first one, right, get it wrong 3 times, watch that video. And then I think once you kind of do 1 or 2, then it starts making sense. All right. Do you guys want to do a division problem or do you feel good about this concept? So move on or divide. Those are your options. Whoever types first gets to vote, and that's what we'll do. Okay, you want to divide? Let's divide. So I like to write my division problems vertically because that's kind of how I roll. So we're going to make this 6.24 times 10 to the 8th divided by 3.17 times 10 to the 2nd. All right, so division is slightly different than multiplication, but the concept in terms of significant figures is the same. So we start by dividing our numbers in the front. So we take 6.24 divided by 3.17. And it does not come out nicely, so we're going to just, take it a couple places. So you should get okay. And I that's not all the digits, but I just stopped there. And what am I going to do to my exponents in this problem? Right? Division is the opposite of multiplication. And when we multiplied, we added our exponents. So if we're doing the opposite of multiplication, right? Exactly, we're going to subtract. And it's always the top exponent minus the bottom. So we're going to take 8 minus 2, which gives us an exponent of 6. Now, in this case, we are in scientific notation, so life is good in the neighborhood. How many significant figures do we want to use in this particular problem? Anybody want to guess? 3 is exactly right. And I made this one a little bit easier in that if you look in the top, 1, 2, 3, in the bottom, 1, 2, 3. So since they both have 3, that's what we're going to use. So if I go 1, 2, 3, I look one number past, 8 rounds up, so I end up with 1.97 times 10 to the 6th. And that would be your answer that WebWork would want for that particular problem. Okay. And of course, if you get stuck on any of these, feel free to shoot me an email, because if you're typing in 1.9684 or whatever, I can respond back pretty quickly and say, hey, you need 3 significant figures, so round, whatever. It's a pretty easy fix if you get stuck. So, okay, any other questions on scientific notation? All right, then we're going to move on to section 4, and section 4 deals with per capita. There are some, trying to think, I think it's in the middle of section 4. There's a table about homicide rates in 2012. It's really good at creating per capita and working in scientific notation and changing the rates. I would definitely recommend watching that video in the middle of this section because it's some good practice with things. Anyway, per capita is ratios. We're going to play with ratios. But when you get to per, right, per is the division bar, and capita simply means person. So when you're finding something per capita, you're really just finding something per person. So in this example that I have down here, okay, so the definition of per capita is simply per person. So if we have 240 TVs in my family and 78 family members, how many TVs per capita? When you're thinking about how does this ratio look, remember that per is the fraction bar. So TVs come first, TVs. Per is the fraction bar. Capita means people. So you would put the people on the bottom. TVs over people. So in terms of number, well, in this particular example, I have 240 TVs and I have 78 family members. This is not a meaningful ratio. This is just the beginning, right? We want to know per person. So how do I take this 240 TVs per 78 people and change it to be per one person? What do I have to do? Exactly, Matt, exactly. We're going to divide. So we take 240 divided by 78. And that gives us roughly, let's round to 2 decimal places because it doesn't tell us here. Good. 3.08. And if you're still thinking about that as a fraction, it's over 1. So for every one person in this family, we have roughly 3 TVs. And if I think about that, when I owned a house, that was true. I had 3 TVs in my house and I lived by myself, right? I moved into a smaller apartment. Now I only have 2 because I just ran out of room, right? So that's what this means. There are 3 TVs per person in this family. It's a whole lot easier to write a meaningful sentence when you have a smaller ratio, right? You have smaller numbers to deal with. And remember, sometimes it helps if you write the ratio in words first, because then when you go to write your meaningful sentence, you know that this top number represents TVs and this bottom number represents people. So there's 3 TVs per person in this particular family. Okay, I want you guys to try one of these beauties. All right, give that one a go, and we'll talk about it in just a moment. All right, so Logan gave us an answer. So if we're thinking about this, a local pen company produces 23 million blue pens every year. If the population of the town is 540,000, how many blue pens are produced per capita? So we've got blue pens, 23 million. And we've got 540,000 on the bottom. Now, I got to be honest, I added this one late. Yeah. Okay, how do we get that? Because there's a couple different ways you can do it, right? You can type that into your calculator if you know how to use your calculator and just roll with it. Or you can use scientific notation. Did you guys use scientific notation, or how did you do it? Logan, do you want to share how you got, like, did you just use your calculator and plug in the numbers, or did you change them to scientific notation calculator? Okay, I want to show how we can do this with scientific notation just because I think that's the section that we're in, and that's my job. There's nothing wrong with just using your calculator, plugging it in. Like high five, that's totally fine. But some people like to kind of, apply what we've done. So 23 million is 6. So that's 10 to the 6th. Again, we want the 23, it's bigger than 10. So if I move my decimal over 1, my exponent's going to go up 1. So I end up with 2.3 times 10 to the 7th in my numerator. In the denominator, 1, 2, 3, 4, 5, I end up with 5.4 times 10 to the 5th. Right? So then if you divide 2.3 divided by 5.4, you get 0.4259 times 10 to the 2nd. And then you go back to standard form, right? 2 places to the right, and there's your 42.59. So you can use scientific notation, and that's where I say it's easier to type in 2.3 divided by 5.4 in your calculator than trying to figure out how do you type in 23 million. You know, some people have a calculator where you can do times 10 to the 6th and type it in easily, but if you don't know how to use your calculator, that's not the easiest way to do it. So you want to make sure you're using a method that is the easiest for you, you know? So, okay, anybody else have an issue with that one? Brittany, Matt, Morgan, you guys all okay on that answer? That's good. Good. Okay, excellent. So that's, I mean, as long as you remember that per capita means write a ratio with people on the bottom and simplify, there you go, right? That's the whole entire concept of per capita. So it's not, you just have to remember what it means. The definition is key. Okay, in section 4, we also get to the negative exponents of scientific notation. So let's play with that. I'm going to let you guys try these two because we've already done scientific notation once, but now we're just going to go the other way. So see if you can try those two. Okay, we got some answers coming in. Okay, so let's look at the top one. Hopefully you recognize that this is a super small number. And if you have a small number, we need a negative exponent. So let me get my color here. All right, we want our decimal point to be there, 2.3 times 10 to the 1, 2, 3, 4, 5, 6. It's going to be a 6, but because it's small, it is negative. So yeah, so Morgan, you can get rid of those question marks, have a little confidence, very good. And then in the next one, because the exponent is negative, that means our number gets smaller. If it gets smaller, you move it to the left because that's what makes a number smaller. So 1, 2, 3, make sure you've got that point, then 0093, just like Brittany has in the chat box. And WebWork does like a 0 in front of that. So just FYI, that is helpful. Because otherwise it'll count you wrong if you don't have a 0 in front of your decimal point. All right, questions about scientific notation with negative exponents? Okay. One thing I want to add in, let me back up. This is just kind of a little aside. If you, let's say you either multiply or divide, it doesn't matter. And let's say we divide and we end up with an answer of 0.423 times 10 to the 6th. All right, that's not scientific notation. And you can see the number in front is small, right? It's less than 1. Less than 1 is small, small is negative, negative goes down, right? That concept. So I move my decimal point one place to get it between 1 and 10. But because 0.423 is small, it's less than 1, it's negative, it goes down, our exponent goes down by 1. So we would end up with 4.23 times 10 to the 5th after I move my decimal point one place. Does that concept make sense to everybody? in regards to how we did it before, right? If it's positive and it's big, it goes up. So if it's negative, it's small, the exponents go down, right? If you understand one, sometimes it's easier with the other because it kind of follows the same pattern type of a thing. But okay. Don't seem to have any questions, so we'll move on. All right, so we're up to section 5. Is it? Okay, doing great on time. All right, so proportions. Most people remember solving proportions in high school or the last time you took a math class because proportions are everywhere. So here's a basic proportion. A proportion is a comparison of two ratios, right? A ratio being two fractions. So do any of you remember how to solve proportions from back in your mathematical days? Cross multiply, absolutely. So we've got a little bit of math that we have to remember how to do. So color. Cross multiplication means you take the denominator of one fraction and you multiply by the numerator of the other. So 12 times 2 is 24. That is set equal to the denominator times the numerator of the other side, which is 3x. All right, talking about the equal sign breaks up each side individually. So now if I want to get x by itself, how do I get x by itself? Divide, exactly. We always want to divide by the number in front of x. So because 3 is in front of x, those cancel out, and I'm left with x is 8. Now, gone are the days where you're just going to get a proportion you have to solve, right? We are going to deal with story problems. And with story problems, like, you have to set them up. And that's the hard part. I've never had anybody who really struggles solving the proportion. It's setting up the proportion that tends to cause people pain and suffering and horror. And one thing that I want to stress is that every proportion can be written 4 different ways correctly. So when you're looking at this, I'm going to label my proportions so that you can see, because consistency is the key. You have to have things set up in such a way that they're consistent. And there are 4 different ways you can do that. So if you see things a little bit differently than I do, that's fine. When we cross multiply, as long as your cross multiplication and my cross multiplication are the same, then our ratios are fine, right? Because there's 4 different ways to do it. So we're going to do this one together. Sally ran 4 miles to every 3 miles run by Billy. If Billy ran 254 miles in 2016, how many miles did Sally run? Okay, so basically I'm comparing Sally to Billy. And I'm all about labeling because I got to see what I'm dealing with. So my left ratio is going to be all about Sally, and my right ratio is going to be all about Billy. So I know that the first sentence, it's kind of like the breakdown. Sally ran 4 miles to every 3 miles run by Billy. So maybe this is, daily, and then the other one is yearly, if I need to label those. And then it says, if Billy ran 254 miles, well, that's total. So Billy's total is 254. So what is Sally's total? Right? So that's kind of the setup. And remember, there are 4 correct ways to set up this exact proportion. But if I set it up this way, when I cross multiply, I get 3x. And then I take 4 times 254 and get 1016. As we mentioned earlier, we divide by the number in front of x, which is 3. And unfortunately, that number is not divisible by 3 evenly. So we end up with roughly 338.7 miles. And then we have a meaningful sentence. Sally ran 338.7 miles in 2016. Right? We know that's the sentence. And so that's kind of also helps with your labeling. If this is what you're finding Sally's yearly total of miles, you can use that in your sentence. Okay? Who's got a question with any of what I just did there? Or comment, concern, suggestion, thought process? It's really recognizing what you're comparing, because that's what proportions are. Proportions are comparisons. So as soon as I recognize that I'm comparing Sally and Billy, then I can start putting in numbers and seeing how things go together. Okay, I want you guys to try one. Try this one. By the way, this is made up data. I have no idea if these are correct. So Logan's got 513.3 miles. Everybody else get that? Get something else? So if you struggle with story problems, right, when you read this, the distance from Cleveland to Columbus is 140 miles, but just 1.5 inches on the map. If the distance from Washington, D.C. to Pittsburgh is 5.5 inches on a map, how many miles are between the two cities? So, I'm looking at Columbus to Cleveland, and I'm looking at Washington to Pittsburgh. I'm comparing two different, drives, if you will. And then we're talking about miles, or actual distance, to inches, which is map distance. So Cleveland to Columbus is 140 miles, but only 1.5 inches on a map. Washington, D.C. to Pittsburgh is 5.5 inches, so that has to go on the bottom. Actual miles goes on the top. So when I cross multiply, I get 1.5x equals 770. Divide by 1.5, and there is Logan's 513.3 miles between DC and Pittsburgh. And again, all made up data because I don't know what's true. And I didn't look it up. Questions, comments, concerns, suggestions, cuss words. What do you think? This is where, okay, so Morgan says she's good. Morgan's good, okay. What else? Brittany, Matt, Logan, give me some. This is overall on today. Brittany says she's good, okay. Matt's good. I've got one more. For some reason, my thing. I think I only have. Yep, I only have one more sample with that, with proportions, and then we're going to be done. So this is the last one for the day, and this is playing a what if game. All right, so you can have all of the data. So this is all made up data again. So let's say that Michigan raised $16,500 with 250 people, and Ohio raised $24,750 with 300 people. So these are the actual people and how much they raised. So if we look at the next sentence, if Michigan were proportional to Ohio, how much money would they actually raise? So when you're playing the what if game, okay, we're comparing Michigan to Ohio, and the two things that we have to compare is money and people. So the question says, if Michigan were proportional to Ohio, how much money would Michigan raise? That's the unknown value. We're trying to say, how much would Michigan raise if they were like Ohio? So the other three numbers, we use actual data. Well, Ohio raised 24,750. They have 300 people. Michigan has 250 people. So if Michigan had raised at the same rate as Ohio, well, then 300x would equal whatever this number is, 6,187,500. We would divide both sides by 300, and Michigan would have raised $20,625. This is what they would have raised if they were like Ohio. They actually only raised $16,500. And then you have a comparison. Michigan would have raised $4,125 more if they were proportional to Ohio. Boom. So there are times that proportions can be used. I call it playing the what if game of taking data that you already know, but messing with it to see how it could be different, right? We do this with, full-time students at different campuses. This is how many, FTEs you have, head count, blah, blah, blah. If you were proportional to Fort Wayne, how many people would you have, right? This kind of stuff is done all the time because that's how you can really compare easily. You can't really compare. We had different numbers of people, this Michigan and Ohio example. But if you set them up and make them proportional, you can see whether or not they're in line. And we get more into that in section 6, which is next week, which is applications of proportions, and then dealing with percents in section 7. So if you understand just the basic setup, you can probably think through this. Just make sure with the what if game, I always start my proportions with what do I need to know? And in this case, I need to know how much money Michigan would raise. Okay, then that's where my X goes, and everything else you just fill in around it. So it's not too bad. It's just a matter of kind of really thinking through what the problem is. So, all right, that is the end of this. So just going back and thinking, I don't know why my PowerPoint is now not responding. Awesome. But does anybody have any questions, comments, concerns about anything from this week? I will be periodically today just trying to get on web work and snipping it around and seeing how it works. If it causes me distress, I will back up the web work to due date. But again, I don't want them to get backlogged. So I'd like to get at least that one knocked out. But if it's not working, I will totally back it up because it's not fair to you guys to be frustrated that you can't get your homework done because it's not working. So make sure you're continuing to communicate with me if we have those issues, and we'll kind of make things go from there. But that's the end of the live session of material. So obviously there's a lot more examples in your packet. Section 5 has a ton of story problems in it. So it might be beneficial, to go through, try to do a couple of those, and then watch a video or two, just to make sure you really understand how to set them up, because that's crucial. You got to make sure you know how to do that. But as always, if you have any questions, shoot me an email. I do ask that you give me some time to respond. I do have other things going on besides just responding to emails, so sometimes it may take me a couple hours. There is a certain time every night where I say, okay, I'm done with work, because otherwise I'll work all the time and it's not good for my health. So there will come a time tonight where I just will not check email anymore. So if you email me at 8 o'clock, there's a good chance I won't read it until tomorrow morning. Just putting that out there. So yeah, but anyway, keep them coming. Just be aware that I might not get back to you right away. So it might take a few hours. So if you guys don't have any other questions, I'm done. You can head off and get working on your homework or do something else fun this afternoon. And yeah, we'll see you again next week for sections 6 and 7. If you have any comments or suggestions or feedback or anything to make these live sessions better, as always, just, you can either put them in the discussion board or shoot them to me in an email, and always trying to make things better. So just let me know what I can do for you. So thanks for coming. Have a great day. And if you have any questions, I'll stick around for a little bit to answer them. Can I see a division problem using negative scientific notation real quick? Sure. I'm not sure. Ooh, look at that. We're going to use this background of blue or black because I don't know what's going on with my computer, but it'll be fine. So yeah, if we would take, let's say 2.3. Oh my gosh, I love this. We should start doing all the lessons like this. Times 10 to the 4th. And let's divide that by 5.8 times 10 to the 6th. We're really going to get negative here. All right. So the process is the same in that we start with the dividing of numbers. So 2.3 divided by 5.8 gives us what? And if you're good and you don't want to stick around for this, you're more than welcome to leave. Right? I'm just going to take questions and do anything anybody else wants to see, do more problems, whatever. But when I divide these numbers, I get a small number, right? I get 0.39655, and we could go on forever, right? Now, when I do my exponents here, again, we're dividing, so we subtract. So my top exponent is 4, and I'm going to subtract 6. 4 minus 6 is negative 2. Okay, so that's what we did earlier. Nothing new, just, different numbers. Okay, well, the front number here is less than 1, right? It's small. Small means negative. Negative means down, right? Decrease. So if I need to move this over 1 to put it in scientific notation, well, it's small. That means my exponent is also going to go down 1. So I end up at 3.9655 times 10 to the negative 3rd. If you think about a number line, if this is 0, if I'm at, here's negative 1, negative 2, I got to go down 1 more. That gets me to negative 3. And if we think significant figures, this one has 2, this one has 2, so I need 2 significant figures. So 1, 2, I look at the 6, 6 rounds up, so my final answer would be 4.0 times 10 to the negative 3rd in scientific notation. So is that what you were thinking, Brittany, when you were? I made it as negative as I could make it. Oh, right on. Yeah. It's definitely basically just very similar to this, that if we have, do you remember if the negative exponent's in the top or the bottom? I think it's in the bottom. We'll talk about it either way. Okay, so in a problem like this, if you have a positive in the top and negative in the bottom, so same concept, 3.4 divided by 1.7 is 2. I made that one easy. Since you're dividing, you always start with the top, so 4 minus, and in this case, negative 2. So if you think back, I don't know what year they talk about this, but 2 negatives is a positive, right? You add the opposite. So this would, in this case, would give you an exponent of 6. Because 2 negatives makes a positive. Now, if if you had, we'll stick with 3.4. If you had the negative exponent in the top and a positive exponent in the bottom, just for fun, right? Again, we do this, we get 2. Now we would take negative 4 minus, in this case, 2. And negative 4 minus 2 gives us negative 6. You just have to remember you're always subtracting. You always start with a subtraction sign between them. And then if you have another negative, 2 negatives makes a positive. But in the second example, the 2 was positive, so you're just subtracting it. So yeah, no problem. No problem. And that's why it's helpful to at least do some of the problems before you come. That way, if you have a question, you can do that. Okay, Morgan, I noticed our first exam is due on a Saturday. Do we have to take it on a Saturday? Oh, you can take it the week before. Yeah, this class is actually set up. I need to do the paperwork on that. But the exam is anytime that week. I just make Saturday as the due date because if people work during the week from 8 to 5, not all testing centers are open after 5, so they need to be able to take it on Saturday so they can actually get there. But I recommend taking it as early in the week as you're ready, because otherwise, the longer you put it off, it just creates issues. And also, if you work ahead and you're ready for the exam next week, there's nothing stopping you. Well, right now there is because I haven't done the paperwork. But we will start talking about the exam probably next week. The week after, we'll really get into it hard because it's week 5 where you see the first exam. But yeah, you can totally take it during the week before the Saturday due date. I recommend that. I recommend Saturday being a last resort if you have no other options. Yeah. Yeah. Any other questions? All right. Well, I'll stick around for a few more minutes. So if you decide you do have questions, feel free. Otherwise, thanks for coming. And I'll see you guys again next week. Thank you much. No, as long as you hit submit on every problem, you're good. After the due date is over, I go into web work and I have to write down everybody's, and then I hand enter them into Ivy Learn. So once you've submitted the problems, and you're good to go. Yep, that's all you have to do. Yep. Then the work falls on me. You're welcome. Have a great day.